Hi all, I welcome you all to the next lecture where you will be introduced to the concept of heat transfer. In the previous lecture, we have covered the work transfer and where we have discussed about the work transfer in quasi-static process. Basically, we have derived expression for the PDB work, or we used to say that as boundary work or displacement work. It is applicable only for non-flow processes, and the condition applied was that process should be quasi-static. Apart from that, we have seen different modes of work transfer, and we have concluded with that. And today we will see the heat transfer. So before starting that, let's start with the final ending conclusory part of the previous lecture. So the work transfer was we have written in this way. So W1 to 2 or 1 W2 is nothing but integration between 1 and 2 PdV. Right. Basically, this equation is valid only for three conditions. First condition, first condition is the process is quasi-static. Second condition, the process takes place in a non-flow systems or closed system. Third one, third condition for this, work transfer is associated only with the boundary displacement. That means where boundary are movable or boundaries are movable, there only you can find out the PDV work. But these two conditions, initial and second condition, should satisfy. The process should occur quasi-statically, right? It should not happen abrupt change. If changes are happening very slowly, so each state passed through via the system is an equilibrium state. If that condition exists, we can find out the PDV, or else we cannot directly get the integration of it. So let's start our next topic starting from that. So next one is heat or heat transfer. By the name itself, it is somewhat related to the temperature, right? So heat is a form of energy which occurs between system and its surrounding by virtue of temperature difference, right? So basically temperature difference is the potential and heat transfer is the flux. As we commonly know, like work transfer, the heat transfer also can be observed only at the boundary. So it is also a form of energy in transit that is going to transfer across system boundary. Another thing is that like work transfer, it also depends on the path or process through which heat transfer is taking place. So as this depends on the path or process, so it's not a property of system. So if somebody wants to say that it is the total heat or total heat content of a system, that statement is wrong, because heat cannot be stored. It is not conserved basically, because it's not a property of system. So as this is not a property of system, so it does not depend on the state basically. If I want to define heat at a single state, I cannot define, because it depends on the type of process. So as this is not a property of system, I cannot write exact differential for that. So this will be inexact differential. So if I want to write change in heat, right, I need to write in this way dou q, right? This is the correct way of representation, or dou q. This one is also correct, but not like, I cannot write like dq. This will be wrong because it is not an exact differential, because not a property of system, right? So there are basically three modes of heat transfer, right? One is called conduction. Conduction is the method of heat transfer if two bodies are in direct contact and there is a transfer of heat is taking place between them. Second one, if bodies are separated by an empty space or gas, then the heat transfer takes place by the mechanism called radiation via electromagnetic waves. Right, that kind of heat transfer is known as radiative heat transfer. There is another third method of heat transfer, that is called convection heat transfer, in which heat will get transferred from a wall to a moving fluid system. If any moving fluid system, right, if fluid is moving near the wall, it will take away heat from the wall, and such kind of heat transfer is known as convection form of heat transfer. These are three modes of heat transfer, and most of the engineering, you know, processes will occur between these three types of heat transfer. So heat basically is denoted by Q, right? Denoted by Q. So unit is again like joule or Newton meter. So total heat is, we can say, joule, right? Joule. And specific heat, if you are talking about specific heat, that is total heat by mass. So when we are writing specific heat, that will be Q, and Q will be in joule per kilogram. Right? Sometimes somebody may ask, what is the rate of heat transfer? So rate of heat transfer is nothing but heat transfer per unit time. Then unit will be kilowatt. Usually it will be kilowatt, right? So total heat transfer per unit time will be called as unit kilowatt. That you keep in mind. So as I said, it is a boundary phenomena. So one can observe heat only at the boundary. If the person is inside the system, he will not sense any kind of change, right, due to the heat transfer to or from the system. So if he is at the boundary, he can easily see there is a change, there is something heat which is going into the system or is coming out of the system. So it is a form of energy in transit. So as it is energy in transit, right, that means it's not a property of system, basically, keep in mind. So like work transfer, heat transfer is also not a property of system, right? So as we have denoted something called, in work transfer, we have said if there's a differential pressure is existing, right, in the system or between system and surrounding, there will be work transfer, right? Keep in mind, in order to have a heat transfer, temperature gradient must be either within the system or between the system and surrounding. So the mode of energy transfer by a temperature gradient is only called heat, and all other interaction apart from the temperature difference will be termed as work. And basically this thermodynamic deals with the study of only these two effects, work and heat transfer. Heat transfer will happen only when there is a temperature gradient, and rest of the thing, whatever interactions are happening, that will be termed as work transfer. So work, as in previous lecture I discussed, there are various kind of works, right? Electrical, magnetic work, shaft work, pedal wheel work, steering work, right? Magnetic work, etc., etc., etc. There are various kind of works. If you add everything, that will give us the total work transfer. But heat transfer, the primary condition is the temperature gradient. So whenever there is a temperature gradient, there will be temperature change, there will be heat transfer. So any process in which there is no heat transfer to or from the system, and such kind of process known as adiabatic process, already got defined. So when somebody asks you, define an adiabatic wall, it is a wall which does not allow any heat transfer to take place either inside or outside. That is called adiabatic wall, right? There is another wall that's called diathermic wall, which will allow the heat transfer to take place, right? That is called diathermic wall. Clear? So usually I said, whenever there is a temperature difference, there will be heat transfer. So if I want to represent that over here, right, so this is temperature and some property change will take place here, we cannot define. Basically this is nothing but due to the heat input and output, there will be entropy change. So entropy, as we have not discussed about till now, so I am representing that by some factor that is called x, that is going to vary. So wherever there is a temperature gradient, there will be some change which is happening to the system, and here also some process is taking place between point 1 and this is point 2. So if I draw like this, right, and this is the temperature gradient basically which I was talking about. So this is T1, this is T2, and this property changes x1 and x2 is taking place. So area under this curve basically will give us the heat transfer. So area under the curve over the plot P and X. At present, you can take this as X. When we cross the second law of thermodynamics, they will come to know what is this X. X is basically entropy that we defined as S, capital S. So area under the curve of the Tx curve represents the heat transfer. So we can write from this equation simply like dou Q is equal to T into dx. Right. So if I want to find out Q122, I can write Q122 is equal to integration between 1 and 2, right? T into dx. So this integration again will be possible only when this process is occurring at very slow rate, or I can say the process is quasi-static. If that's not quasi-static, I cannot find out the transfer. So any quasi-static process will be termed as a reversible process. So only when process is reversible, I can get the heat transfer. Is that clear? Okay, so let's move to the next thing. So this is a path function that basically depends on the path of process. So for different kind of processes, there will be different types of heat transfer, right? Magnitude will differ. Let's go to the next topic, general equation of heat transfer. If we look at general equation of heat transfer. So heat transfer per unit mass is directly proportional to the temperature gradient, because temperature gradient is needed to have a heat transfer. So heat transfer per unit mass is directly proportional to the temperature gradient T2 minus T1. So if I remove this proportionality thing, I can get one proportionality constant C, and this is T2 minus T1, where C is my proportionality constant, also known as specific heat. Specific heat. So heat transfer mass is known as specific heat, right? Then specific heat constant, right? Is a constant, specific heat constant, and T2 minus T1. So this equation I can get. This is specific heat. So unit will be kilojoule per kilogram, right? Kilojoule per kilogram, and this C basically this is specific heat constant, or just specific heat, right? Heat per unit mass, specific heat constant, right? So if I differentiate this, differentiating this, I can get dou Q is equal to dou Q small q is equal to C dt, right? Dou Q C dt, or I can further write from this equation C is equal to, I will write here, wait a minute. So I can write C is equal to dq, not dq, dou q divided by d3. This is known as specific heat, right? Specific heat. Specific heat. So specific heat basically, when we are defining specific heat, is the amount of heat transfer required to make a unit rise of temperature for a unit mass of substance. So if I supply that much amount of heat to a unit mass of substance, there will be unit rise of temperature. That is not a specific heat, right? So if it is a specific heat, unit will be just kilojoule per kilogram Kelvin. So the specific heat unit is kilojoule per kilogram Kelvin. So most of the solid, if I heat it, it will melt, and then again it gets solidified. For most of the solid, if I am heating and melting and cooling it, there will be very less change, appreciable change in pressure and volume, right? So for them, specific heat will almost be the same. So let's suppose, for example, if I consider liquid, for liquid also there will be very negligible change in specific heat with the change of the parameter. So for water it is just 4.2 kilojoule per kilogram Kelvin, or sometime it will be given 4.187 kilojoule per kilogram Kelvin. So this is for water, that you have to remember. So for water is 4.2 kilojoule per kilogram Kelvin, or 4.187 kilojoule per kilogram Kelvin. So for liquid, definitely there will be very less change in specific heat with some other pressure and volume. So there will be only one specific heat. But for the gases which are highly compressible, right? For gases, heat transfer may take place at constant pressure and constant volume, right? Constant pressure or constant volume. So specific heat will be defined based on constant pressure and constant volume. So if we are defining in that way, right? If we are defining in that way, we can define in a very simple mathematics like what we have used there, right? So if I say specific heat at constant pressure, which is driven by Cp, so specific heat at constant pressure, it is amount of heat transfer to a unit mass of substance, right, to raise its temperature y unity one process is taking place at constant pressure. Such type of heat transfer is known as specific heat at constant pressure. So you can write that is Cp is equal to dou Q divided by dt at constant pressure. So this is my Cp basically. So as Q is not a property of system, right? Cp will also not be a property of system if we are defining based on this heat transfer, right? If we are defining it specific heat, then specific heat will not also be a property of system. So for air, right? For air, Cp value is fixed. This is nothing but 1005 joule per kilogram Kelvin. That you keep in mind. The specific heat at constant pressure. Similarly, specific heat at constant volume. Specific heat at constant volume, that can also be defined in a similar way. So specific heat at constant volume is defined as the amount of heat transfer through a unit mass of substance to raise its temperature y unity, while during this process volume remains constant, and such kind of heat transfer is known as specific heat at constant volume. So this can also be written as Cv is equal to dou Q divided by dt constant volume. And for air Cp value is fixed, that is 0.718 kilojoule per kilogram Kelvin. So Cv for air is 0.718 kilojoule per kilogram Kelvin. But this is clear. So general definition of specific heat is here, but for liquid it will be only one value of specific heat, because for liquid there is very negligible change in pressure and volume. Right, with that C value will change very negligibly small. There will be only one fixed value of specific heat. But gases are highly compressible. For that cases, right, heat transfer may take place with constant pressure or constant volume conditions. So these two specific heats need to be defined for the gases only. If it's a liquid, there will be only one specific heat. So this is whether this is clear. Now next topic is heat capacity, right? Heat capacity. Heat capacity, right? How will we define that? So basically, heat capacity is nothing but it is a product of mass into specific heat. Product of mass and specific heat is known as heat capacity. So it's very simple, right? So heat capacity, capital C, will give either mass into small c, right? So based on this is called heat capacity. So when I'm writing the heat capacity, it will be just kilojoule, right? Kilojoule, and what will come? Kelvin, right? Kilogram cancel, kilojoule per Kelvin, right? Or similarly, Cp can be defined m into Cp, right? And Cv, capital Cv is m into Cv. So like that we can define the heat capacity, right? So as I said, heat is not a property of system, so we cannot say it is a heat capacity of a system. But certain fluid may contain this much heat. We can say heat capacity will go by the product mass into specific heat. Let's go for the next topic. Sometime they used to ask, right, what is a molar space, molar, right, molar specific heat. Here we were defining specific heat based on the mass in kilogram. Here we have to define based on the mole, right? So molar specific heat will be defined as the amount of heat transfer to raise the temperature of a unit mole of a substance by unit rise in temperature. And the unit for this specific heat, molar specific heat, will be kilojoule per kilogram kilomole K, kilojoule per kilomole K. So when we are defining for specific heat for constant pressure, molar Cp bar is the molar specific heat at constant pressure will be given by the molecular weight into Cp. Similarly, Cv will be written as molecular weight into Cv. So these are the molar specific heat, and unit will be kilojoule per kilomole Kelvin, right? So molecular mass, atomic mass, or molecular weight. So for air, right, for air we know molecular weight is 29, right? Usually we consider 29 mole by mole, right? So 29, if you multiply 29 by Cp and Cv, right, I can get the molar specific heat at constant pressure and molar specific heat at constant volume I can get. So molar specific heat is also over. Let's look for the sign convention. Sign conventions. What sign conventions we need to follow? Like in work transfer we have followed sign convention is work is done on the system will be considered as negative, and work done by the system will be considered positive. What will be here? So this is my system, right? Any system, and some heat is coming and some heat is going, right? This is my system and this has surroundings. Here it is opposite. If heat is coming to the system, that means it is increasing the energy of system. So in system will feel like energized. So heat which is coming into this system will be considered positive, and heat which is going out of the system will be considered as negative. Heat which is coming in the system is positive, heat which is going out of the system will be negative. If heat is getting transferred from the system will feel like exhausted, right? So it's losing its energy, so that will be considered negative. This is very simple sign convention. If heat is getting added to the system will be considered positive, and heat is going from the system or transferring, rejecting from the system will be considered as negative. So this is a very simple sign convention, right, need to be followed for the heat transfer. So any doubt to here? I don't think so. So let's go for the next topic, right? uh Specific heat we have defined. Let's next one is latent heat. Latent heat, actually latent heat is the amount of heat transfer required to make a phase change. If I want to make the phase change from liquid to solid, solid to liquid, or liquid to vapor, right, I need some energy to be to make it happen, right, at constant pressure and temperature. Condition is it is amount of heat transfer required to make a phase change at constant pressure and temperature. Condition is constant pressure and temperature. So if we look at whenever any substance undergoes a phase change, it requires some external energy to counter the potential energy stored in the intermolecular forces among atoms. So atoms initially will have some potential energy, so it has to encounter that potential energy in order to make the phase change, right? And that energy basically is called latent heat. So there are three kind of latent heat, as there are three kind of phases: liquid, solid, and vapor. So based on that we can define three types of latent heat. So latent heat of fusion, fusion, right? This is regarding solid. So it is the amount of heat required to make a phase change from liquid to solid, or it is the amount of heat transfer which will be rejected when a solid is getting transferred into the liquid. So whenever the phase change is happening, this much amount of heat will be liberated, either it will be taken inside or it will be going outside, and such heat is known as latent heat of fusion. Latent heat of fusion. So if for ice, if we look at latent heat of fusion, it is denoted by L. Latent heat of fusion for ice is 335 kilojoule per kilogram. 335 kilojoule per kilogram latent heat of fusion of ice. So this is the one latent heat of fusion. Similarly, you can define latent heat of vaporization. Vaporization. So here fusion or latent heat of melting, right? Latent heat of melting also will be defined, vice versa, right? So when we are talking about fusion, that means it is a phase change from liquid to solid, right? So the amount of heat required to make a phase change from liquid to solid. And when latent heat of melting you are defining, that means it is the amount of heat transfer to be liberated, right? When it is transferring from solid to liquid, right? Last one, latent heat of vaporization, is the amount of heat transfer required to make a phase change, right, from liquid to the vapor. Similarly, latent heat of condensation, right, opposite to it, it is the amount of heat transfer which will be rejected from the system to make a phase change from vapor to liquid at constant pressure and temperature. Keep in mind, whenever defining latent heat, you have to add this term, at constant pressure and temperature. Next one is latent heat of sublimation. M-A-T-A, sublimation. If you write like this, it will be sublimation. It is the amount of heat transfer required to make a phase change from solid to vapor, directly from solid to vapor at constant pressure and temperature. That is heat of sublimation is defined as amount of heat transfer required to make a phase change from solid to vapor at constant pressure and temperature. Is that clear? So this is the regarding the latent heat. Latent heat will be denoted by L. So for different substance, it will have a different value, right? So latent heat of fusion, vaporization, sublimation, or you can say latent heat of melting, right, condensation and sublimation you can define. So latent heat is also over. So this much is enough for heat. Now we will compare both, right, because that is also needed. So comparison of heat and comparison of heat and work. First is similarity. First we will see what is similarity. So similarity, we can relate both are energy interactions, right? Both are energy interaction. Any closed system can interact with its surroundings either via heat transfer or by work transfer. Second similarity is that both are the form of energy in transit. That means both will be observed only at the boundary of the system, or we can say both are the boundary phenomena. Third similarity is that both work and heat transfer are the path function. That means the magnitude of work and heat transfer depends on the states, right, or process through which the change of states taking place from initial to the final condition. These are the third conditions. Fourth similarity is that both work and heat transfer do not have any effect at this state. If you want to define a work at a particular state, you cannot define because it's not a state function. Similarly, heat cannot be defined at a single state because it's not a state function. They are path functions. So for a process and path only we can define the work and heat transfer. They cannot be defined for a state, right? So they do not have any meaning at this state. So these are basically the four similarities, right? If we look at the dissimilarities, right? First is similarity, dissimilarity. If we look at the dissimilarity, first and main important dissimilarity for heat is heat transfer will occur only when there is a temperature gradient, right? And work transfer will happen for all the changes except the temperature gradient. So whenever there is a temperature difference, there will be only heat transfer, and apart from temperature difference, anything, any phenomena, any changes happening, that will be termed as work transfer. Second, what is similarity? Area under the pressure volume curve, right? Area under the PV diagram represents the work transfer, and area under the TX diagram, TX, and later on we will define TS, entropy, right? So area under the PV diagram represents the work transfer, right, for a non-flow process, and area under the TX represents the heat transfer. Third dissimilarity is heat is a low grade energy, while work is a high grade energy. How we will define the grades basically? Because low grade energy means it cannot be completely converted into mechanical work, or work can be completely converted into the heat. If I want to convert work into heat, it will be completely convertible into the heat. But all the heat cannot be converted into the work. There is some conversion efficiency that we will come to know in the second law of thermodynamics. So heat is a low grade energy and work is a high grade energy, right? So as a conclusory statement today, what all things we have covered. I have introduced you regarding the heat transfer concept. We have discussed about three different modes of heat transfer: conduction, convection, and radiation. Later on we have seen the specific heat, right, and latent heat. Also the sign conventions were discussed, right, in what way we need to consider positive and negative. And at the end we have defined the similarity and dissimilarity between work and heat transfer. Keep in mind, work and heat transfer both are path function. So don't say they can be conserved. You cannot conserve them, or you cannot store them basically, because these are not the properties of system. So if it is anything which is property of system can be stored, right? Keep in mind. So similarity we have seen, both are boundary phenomena. They will occur only at the boundary. So somebody is saying that I am able to extend the work when I was within the system. This is that statement will be wrong, because when you are inside the system you will not feel anything. If you are at the boundary only, you will be able to sense the changes which are happening to the system. So both are boundary phenomena. That means they are the form of energy in transit. All right. So basically any closed system will be interacting only via these two modes of energy interaction. Sometime work transfer will happen, heat transfer will happen, or both may happen across the system boundary, right? Dissimilarity also we have seen. So with this I am closing the today's discussion. In the next lecture we will see the practical applications of it. We will solve some numerical problems based on the work and heat transfer concept, right? So thank you for listening today's lecture. Have a nice day. Good day.